working in the chemistry department at Bilkent University, so I'm working my research, which was established 11 years ago in 2006. So I will give it not a single line code, so it's going to be easier to follow with you. So we're in catalysis, namely reagents catalysis and surface science in terms of understanding catalytic functionalities of nanosystems. And two different relevant to my talk, these are environmental friendly processes, that means environment and energy. So we will try to see how we can use nanotechnology and catalysis for environment and energy. So before I start, I would like to just actually thank the people who did the work. So I didn't really do the work, so this is my team. So the postdocs, grad students, and undergrads, and they're all members of the chemistry department. So I will start with a couple of paintings that I really like. So if you go to Madrid, Spain, so if you go to the Prado Museum, you will see a huge picture of Diego Velázquez. This is one of the masterpieces of probably Romantic era. So Diego Velázquez, in this famous picture called Las Meninas, is actually picturing the Infanta Margarita, the young princess, and this is considered to be one of the masterpieces. Picasso, Dali, they were obsessed with this picture. Picasso made like tens of replicas. Dali is an obsessive person, made like 30 replicas. So this is what we do in science. So a very complex picture, foreground players, background players, shadows, pictures. So if you want to find out what is the most important aspect, critical player, the active side of catalysis in this picture, you may kind of think that the Velázquez himself is picturing the young princess. So you think that this is the most prominent figure in the game. However, in the background, there is a mirror. You can see the reflection of King of Portugal to the fifth. And actually, what the painter is painting is not what we see in the foreground. The most important character is in the background. Unfortunately, this is the game in catalysis. Most of the time, when you spectroscopically detect a species that's most likely not that much relevant to catalysis, that's an intermediate, that stays longer. If it has a long lifetime, that means it's like that's a dead end. That means, like in your Picasso's picture, this is more like an experiment of reality. So reality is complex, very complicated. Experiments are much more simple, like the cubic impressionist version, the monochromatic version. So experiments distort reality and they give us data. So you have to interpret the data to find out the king in the background, which is difficult. So most of the times you fail, and you publish papers and papers over the same catalytic reaction for decades. So therefore, if you want to understand catalysis, it's difficult, it's complicated, especially if there's catalysis. So you have to attack the problem from different fronts. So that's what we try to do in our research group. It's challenging, but we try. So what you have to do is you have to try to understand reaction mechanisms at the atomic level. So these are difficult experiments that require ultra-high vacuum and very valve-defined, valve-defined surfaces, like single-crystal surfaces, monolayers of metal oxides. And you have to use specific surface-sensitive spectroscopic imaging and diffraction techniques. So we do a bit of ultra-high vacuum surface science. So hopefully if you have some chance, please feel free to visit our labs. We will have some demos in some of our labs next week. So you're more than welcome to visit our other labs in the chemistry department. And in addition to that, these are of course very well-defined systems, but they're not that much relevant in terms of operando real catalysis, so you have to just level up your game and go to realistic materials, which are mesoporous, high surface area, complicated, but active. And that's not even enough. Understanding physical chemistry of the surface functionality is nice, but if you don't run them under operando conditions using catalytic tests, you never just understand whether that's a material or a catalyst. The difference between a material and a catalyst is money. So whether it runs, test activity and selectivity, that's the differentiation between a material and a catalyst. You have to just demonstrate that these are actually running with reasonable activity and stability under realistic conditions. And while they're doing that, nowadays the modeling is becoming more and more useful. That's the functional theory and whatnot, microkinetic modeling, and we also collaborate with physicists to get some help on that. So basically, the different parts of the jigsaw puzzle, if you just combine them, you can have a chance of perhaps getting an idea of the big picture. So this is kind of like what we try to do. A real catalyst is very complicated at the nanometer scale, so it's got, a commercial catalyst might have about quarter of the periodic table in its contents. They're very combinatorial. It's almost like a black art. They're made by optimization processes, very complex creatures. You have active sites, promoters, poisons, support materials, structural promoters, electronic promoters, so on and so forth. Very, very complicated. Even if you use spectroscopy and operando measurements, the data is so sophisticated and convoluted, it's very difficult to understand. So thus, what we try to do is, yet we appreciate the fact that this is the active catalyst. We try to simplify the game in a reasonable fashion, so we try to make some educated guesses about the active sites. So then we do experimental modeling, that means we just simplify the complexity, and we try to do atomically well-defined surfaces where we just study only the active site. Then we just develop our game, we increase the complexity, for instance, we add a support meter, promoters, and so forth, and we try to just increase complexity in order to just get down to the realistic case, which is not very easy. So we have different types of capabilities in my research group since 2006. We have been building special-made, custom-made systems. So most of the data that you will see here are obtained in special custom-designed chambers. So they're not benched up the system. So because we want to follow catalytic reactions in situ, real time, during the reaction, so they require special case. This is, for instance, our ultra-high vacuum lab in 2008. This is the first ultra-high vacuum multi-component chamber designed in Turkey, all homemade. That can be X-ray photoemission spectroscopy, temperature program disruption, long-range electron refraction, and also infrared reflection absorption spectroscopy to look at single crystal surfaces under ultra-high vacuum with high resolution, everything underwater. And you're more than welcome to visit this. Now it's even bigger, so it's actually a really large instrument. It's all custom design. So we also do more regular spectroscopy. So this is another photoemission XPS system where we look at powders. So the previous setup was dedicated to ultra thin films, which are monolayer thin, sometimes even thinner. We can do 2D atoms or single crystals. But for realistic catalysts like powders, we use a different photoemission spectrometer, which we designed but we didn't build. It was built by Specs company in Germany. Then we have a powder catalysis lab. This is the instrument that you will be using next week yourself. So really nice, fun little system where we can analyze in real-time powder samples, mesoporous nanomaterials. You can call them nanocatalysts. If somebody tells you the word nanocatalyst, make sure that that person doesn't understand catalysis, because all catalysts are nano. So if somebody tells you I'm a nanocatalyst, great, excellent. So these are nanomaterials, of course. These are catalysts. This is also a custom design system where we can look at the powders. These are nanomaterials. In real time by dosing some reactive gases. So in transmission mode, while we're following the reaction with a mass spectrometer coupled to the system, which can be varied as a function of temperature and gas mixture, we can follow the reaction products in gas phase. So while the infrared follows the surface reactions and surface species, the gas phase is detected by mass spectrometer, and you will use them yourself, hopefully, and you will see how we can utilize such a system very effectively. And they require all different types of little designs that we have come up with during time, like sample compartments, optical components, vacuum components, like little dimensions that we have designed all almost made in Turkey. So further to that, we also have photocatalytic endeavors. We do photocatalysis, and we have a photocatalytic flow reactor. Unfortunately, there's actually more over here, but then we just in this particular photocatalytic reactor, we flow gases and we look at the photocatalytic reactions on special powders in the presence of light. Now we have on this one, and we do also even engineering. That means real ground catalytic activity measurements in a tubular reactor where we can dose all different types of gases, and in a realistic catalyst we can follow the GC and the mass spec and follow the products. So those are the capabilities in the house, and the first opening topic will be emission control, environmental pollution, air pollution. You can ask, is emission control still a problem? Air pollution, is that a problem? And probably the answer is yes. So these pictures are taken less than a year ago in Beijing, China. In July, the weather forecast was 35 degrees sunny. Okay, so this is a sunny picture. There are no clouds actually. This is not a cloudy day in Beijing. Forecast is sunny. And there's so much particulate matter and so much NOx in Beijing that you don't see the sun. You can see that I can very well open my eyes. I cannot see the sun, but it's so polluted. So there's a real problem with pollution among the developing world. But you can say, hey, China is not the most developed country in the world. But as you will see in statistics nowadays, even in Europe, there are huge problems. So if you're following the news, in 2015, Volkswagen, had a great scandal in terms of cheating the whole world in terms of NOx, nitrogen oxide emissions. So it turns out that Volkswagen was cheating billions of dollars by making cheap and crappy catalysts and putting in their cars, which are polluting air about 35 times more than the regulated amounts. So actually in 2014, European Union just published a white paper on air pollution. Surprisingly, Germany, and probably Austria too, was polluting air like hell. And I was so surprised. I was like, how come Germany is polluting air significantly? And it turned out that actually these Volkswagen cars, where the engineering and all the emission control system designed by Bosch, pollutes the air 35 times more than regulated amounts in terms of NOx. As a matter of fact, in Europe, there are only 2 countries which can satisfy the regulations. Ireland and probably one more country. All other countries are violating emission control standards in Europe, not in China and in India. Okay? So this is a huge problem. After this was figured out, and by this was a very smart thing, but Volkswagen was doing, they had artificial intelligence. So when you just stop the car can realize that you went into service. So it runs the engine in a safe mode where it doesn't pollute the air. So it cheats. When you're stopping or when you're running in idle mode, the car doesn't pollute the air. So when you're in the service station, you understand that it's in the service station, it doesn't pollute the air. When you're in the highway, it just pollutes the air like hell. Therefore, now we've got new regulations. They're going to measure emissions in real time in the driving mode. So that's coming up this year. And when this happened, Volkswagen actually lost about 18% of the stock value, which is billions of dollars. Now they're facing about, I would say, $20 billion worth of fines and fees. Okay, big business, and that's nice. That keeps us busy. So, what is Turkey doing? So, in terms of total NOx emissions, Turkey is right over here. These are some of the OECD countries. So, Turkey is polluting air, not immediately, but they're much more like the old countries. So, this is total pollution. But if you just look at pollution per capita, that is pollution per citizen, actually Turkey is not polluting the air that much. This is something that we should be happy about, but also we should be depressed about. Why should we be depressed about this? Any ideas? What do you think? So isn't that
good? Enough cargo.
Exactly. We don't have enough industry. We don't have enough consumption. We don't pollute the air because we don't have the industry. As a matter of fact, there is actually a very nice picture that's going to be hopefully coming up. And you can look at the populations. Turkey, this is like 2013, set it down because like 8 million people. In Austria, 8 million. You've got 10 Austrias in Turkey. Of course, the industrialization and the economy and the development, unfortunately, is not there yet. So, actually, from my perspective, environmental, this is nice, but industrial, this is quite depressing. So, we have to be polluting the air much more. I'm not meaning that. So, another thing. Turkish government has been measuring the total NOx emissions over the years. Now this is all broadcast online, real-time. Ankara has 8 different stations. You can monitor the toxicity in air, 8 different locations every minute. If you look at the total NOx emission per capita over the years, you can learn a lot. So what you learn about the, for instance, financial situation in Turkey or economic situation. You see that NOx emissions are increasing, probably economy is growing up, more cars are old, people are driving, people have money, people have jobs. 2008, September, financial crisis, Lehman Brothers go bankrupt, AIG, all that business, Wall Street melts down. You can see boom, going down. And it's going up again, then it's going down again. So actually, and I can measure this in the lab using the chemical NOx analyzer. So I can say, probably I should buy some dollars for that. So of course this is kidding, but there is some correlation, but of course you should not be investing money just based on NOx emissions. So how can we control NOx emissions coming from the cars, mobile emissions? So these are car emissions. We drive cars, all different types of cars. The incoming poisons or toxic gases are nitrogen oxides, NOx, sulfur oxides, hydrocarbons, and CO. And you've got so-called a catalytic converter. This is called a monolith, flow mode. You've got the magic powder. This is actually a ceramic bowl. You've got the Bosch coat over here, which is a catalyst. That's a thickness of 50 microns. If you zoom in with an electron microscope, you've got the catalytic zoo. About 1/4 of the purity table is there. Very sophisticated piece of catalyst. And you've got actually more of them. You've got like 1, 2, 3 of these different chemical reactors working in series. Very complex system. So when you press on the throttle, you've got a chemical plant working in the back of the tailpipe. So what I will talk about today is NOx emissions. Some of these NOx emissions So Toyota company came up with a revolutionary idea about diesel emissions in cars. The problem with diesel emissions is they generate a lot of NOx because they use a lot of air. Air means oxygen. Oxygen reacts with nitrogen and forms nitric oxide as the polluting gas. And diesel cars, although their fuel efficiency is high, they're more toxic. Again, another dilemma, like electric cars. Just because you're driving a diesel, you're consuming less fuel doesn't mean it's environmentally friendly because your exhaust is more toxic. So you have to be careful. So driving efficiency is about 30–40% better, but environmental penalty is huge. Okay? So the problem is, you have to reduce this. You have to do reduction in this. The problem is air is oxidizing with oxygen. How do you do reduction in oxidizing environment? Difficult. So it sounds kind of conflicting. And Toyota people came up with a good idea. They said if you cannot beat the enemy, make friends with the enemy, that means if you cannot do reduction, you can do oxidation. And you can see what? Yes. You can do oxidation, you can oxidize this nitric oxide to solid state nitrates using an alkaline earth oxide nanoparticle. You can store them as nitrates. Then for a very short time, you can pulse in some fuel, extra fuel, reducing the agent for a very short time, for about 5 seconds, and you reduce this nitrate tail, this is called regeneration, on the platinum, and you can get to the happy ending nitrogen. So 95% of the time you're in fuel efficiency, storage, and 5% of the time you're doing reduction. So with about 2% fuel penalty, you can get rid of the NOx. Nice. A lot of problems, to improve. So they're using the, since 1995, they're using a lot of problems. There's a lot of, obviously, room for improvement. Like you can play with the nanotechnology of these metal oxide nanoparticles, you can play with the active sites, their electronic structures, and so on. One of the problems is, for instance, sulfur poisoning. Fuel has sulfur compounds, thiophene, and a lot of different things. And they stick to these active sites, metals, in the form of sulfides and sulfates like hell, and they kill your active site very quickly. So you find out ways of sulfur tolerance. So those are some of the things that we have been doing. First, I'm not going to depth, but we have been doing some surface science experiments under ultra-high vacuum, not at atmospheric pressure, but 10 to the minus 13 atmospheres. So very clean environment. We can follow the surface structure. We can prepare those things experimentally, and we can follow the reactions at the molecular level. You can design multiple catalysts inside the vacuum chamber, and then you can study them without really changing their structure. So for instance, we want to understand some of the important questions. What is the, for instance, effect of particle size of these barium oxide particles? What happens if they're 2D, 3D particle size effect? What about intermediates? Can you form like peroxide, like intermediate species? How they affect the mechanism of NOx absorption and release? What about other metal oxide promoters and so forth? And nanotechnology is fun in the sense that when you make small particles, nobody knows in most of the time what you make. When you look at them, you get surprised. So barium oxide has a rock solid structure, so the chloride structure, shish kebab, right? Tomato meat. So, but if you make the nanoparticles, you can see these are the first low energy electron diffraction data published in Turkey. The first experiment in 1935 in the United States, the first data in Turkey 2008. So you got a bit of delay. 7 years. But what is interesting is these barium oxide particles are not actually like these square-looking ones where it's a rock solid structure. In the nanoparticle form, these are surface diffraction, not X-ray diffraction. So the diffraction comes from the top monolayer of the nanoparticle. Electron diffraction using voltage electrons. And you can see that diffraction patterns are very complex. We just analyze this one. So they're very interesting 2D structures on the surface. And we follow their interactions with anodic species using photoemission spectroscopy, XPS, and we follow what's happening to nitrogen bonds and oxygen bonds. And we verify that there's a new species formed for the first time ever, which was playing a huge game in the absorption mechanism, which was barium peroxide. And when you start to release the NOx after absorption using a mass spectrometer, you put a mass spectrometer here, you heat the catalyst, and you get what is dissolving from the surface, for instance, NO, oxygen, and nitrogen. It turns out that if you design the catalyst, in which case very old platinum, you block the platinum, you deactivate the platinum, you get a certain desorption. And if you have a different catalyst where platinum is exposed, in other words, you get heterojunctions or interface between platinum and barium peroxide, you get a different chemistry, you get direct NOx reduction. So you can form nitrogen. So the chemistry is different. What's interesting is that those two different surfaces are regeneratable. I can switch between those two surfaces by either dosing NOx or heating in oxygen. And that has a quite important relevance in terms of dynamic nature of these particles under catalytic conditions. It turns out that these particles can wet callus surfaces, or they can sinter during the catalytic reaction, so they're dynamic. So these are living creatures, living nanoparticles, which are quite dynamic, not only in chemical functionality, but also in size. So, and we looked at, for instance, we designed different types of nanoparticles with different sizes. We looked at how much they can bind NOx, which is called NOx storage capacity, and we verified that the adsorption strength is higher for bigger particles because you form bulk-like nitrates. That means nitrates can be stored not only on the surface but also in the subsurface. But for small particles, they're weak down, and you can only form surface adsorbed nitrates. So you can actually say that particle size is an effect. And toilet people have mentioned you can add some promoters to mostly improve titania, to mostly improve the sulfur tolerance of these materials. The problem they mentioned was you can add titanium to the system and it becomes sulfur tolerant, but the catalyst dies very easily. So you remedy one problem and you end up with a different problem. And there is a question about why these catalysts were dying when you add a nice promoter to improve sulfur tolerance, and I will get back to the sulfur tolerance business. And we did a simple experiment. This time we coated about 10 monolayer thick titanium film, 10 monolayer, roughly about 300-400 meters in thickness, let's say, on platinum, and you can see this nice 2x2 diffraction pattern, which is specific for titanium overlayer, not for platinum underlying. You don't see the platinum anymore, this is thick enough. Then you put some barium oxide, surface becomes disordered, weak pattern, diffraction pattern disappears. Then you do an accelerated thermal aging experiment. In your car, you run for 100,000 kilometers for 10 years. You don't have that kind of time to lag. So what we can do is, normally these catalysts, they run between 400 to 500 Kelvin temperature range. But we don't have time to wait forever. So what we do is we go to much higher temperatures and we age the catalyst at higher temperatures. So we go to higher temperatures, and in XPS, we look at the barium to titanium surface atomic ratio using XPS in real time. And you can see barium is decreasing with respect to titanium as a function of temperature. And you can say it's just disorbing, evaporating. It's not, because we just put a mass spec, we don't see the barium disorbing. So barium is going somewhere, it's going actually below the bulk. And if you heat it high enough, barium level goes so much down, and the diffraction pattern becomes identical to a titanium-enriched surface, so it's obvious that barium oxide, if you just heat it up, it makes mixed oxides and it's like forms, for instance, titanates and like perovskites and probably spinols, and it goes inside the titanium, and the storage domain, the domain which stores the NOx, your active storage site, is lost. So one of the possibilities for thermal aging in the presence of titanium is probably this kind of mechanism. So by the very simple experiment, you can see, you can answer that. And this is the control experiment. Fresh catalyst, you can absorb and dissolve NOx. That means you can store NOx. Deactivated catalyst, no NOx absorption. Control experiment, a surface without barium, it doesn't do anything. So you can actually verify it. So then you can say these are all like 10 to the minus 13 atmospheres. Who cares? They're not relevant to real technology. What about real materials? The actual work for real materials now is synthesized using sol gel chemistry. Powders, high surface area, 20 meters squared per gram. Mesoporous materials to do the same thing. What is interesting is this is simply EDX picture, EDX mapping, for barium aluminum, titanium aluminum, and barium titanium pictures. And this was obtained by an undergrad actually. And what we have found out is actually this picture, when you look at barium and aluminum, you see red and green signals separated. And they're separated. But when you look at barium and titanium, you don't see green or red, you see yellow, which is a combination color. So that means whenever you have barium with titanium, that means barium and titanium, they coexist on the surface. That's relevant to our experiments in ultra-high vacuum. So we use this curse as a blessing. So it turns out that if you can follow the surface morphology of titanium, if you can make large or small particles, you can control dispersion of barium oxide. That means you can control the healthy functionality by fine-tuning the particle size using titanium. And it does work. If you like aging, if you infrared spectroscopy, we can follow what different geometries of nitrates and nitrites are produced as a function of temperature, pressure, and so forth. So you will do these experiments next week. So don't worry. So you can follow up whether we form bulk or surface nitrates. You can just follow this spectroscopy. I'm not boring you with that. But we do a lot of this surface spectroscopy action in real time when the catalyst is in contact with active sites. So that is right. And by using mass spectroscopy, we can follow at what temperature you dissolve these things, that is stability of these nitrates. And in terms of sulfur poisoning, for instance, we also demonstrated, for instance, these are two poison catalysts without titanium. We dose some sulfur dioxide, we poison them so in infrared you see some sulfate and sulfide peaks, which are irreversible. Once they're down, they never go away. That means they block the active sites, they poison the catalyst, they never go back. Even if you go to 1000 Kelvin, they're still there. So how can we avoid that? If you add a bit of titanium, so you can see these are multiplied by 2, if you heat them up, you can almost completely get rid of all of the sulfates and sulfides, so that means you can actually get some regeneration capability. And you can see how does this work. So what could be the mechanism? We've done some DFT modeling over here. We do titanium, we put some barium oxide on the top, small particles, big particles. As a function of particle size, we looked at SO2 and SO3 absorption energy changes, and we found out that for big particles, SO2 and SO3 absorbs weaker. This is a real significant difference. For small particles, absorption is stronger for barium oxide and titanium. And using this, we can actually explain what's going on. I told that these barium oxide particles are dynamic. They can sinter and wet and de-wet. Their particle size changes. If you have fresh catalyst, barium oxide is small particles dispersed, and the sulfur dioxide absorbs strongly, it poisons. But if you have titanium, if you heat the surface, barium bulks up. When it becomes big particles, absorption strength of SO2 decreases, so they desorb, and when you cool down, it just disperses. So you can actually explain why titanium helps sulfur poisoning. But the problem is these catalysts still die because of turbulence, and eventually it will actually barium will fuse into titanium. It will kill the surface. Okay. So these are just simple-minded stories about what we can do. And recently, it's a PhD thesis, which got completed last year. We can actually prevent this love affair between barium and titanium by putting a different metal oxide, which is titanium-like, but it doesn't have a high affinity to barium oxide. And this is a diffusion barrier, which is actually zirconium. You can make ternary complex metal oxides that I won't get into details, but what I want to say is that it works. I will just show the finding. Look at surface acidity, and I can try to understand why it works. But since catalysts are all about making money, I can show you for instance, benchmark catalysts, the Toyota catalyst, and these ternary oxides, they work much better than the Toyota catalysts under different conditions. Even after the poisoning, they work even better. So, these are really interesting results, and we're going to publish on this. So, in this DMARC business, automotive control, we've been working for more than 10 years, and we've been doing a lot. So, what is interesting now is, these catalysts, they have platinum. And platinum is very expensive. That's why Volkswagen is cheating here, but there's a couple of catalysts, couple of zeolite, and they were saying, hey, it's great, it was a miracle, it was working. It wasn't working. So the problem is we have to get away from platinum. And General Motors company published a science paper, and we had an interaction with them in Detroit. I was fortunate to present something in Detroit, and they also was next to me. We talked to them and we started collaboration. And this is another financial indicator. These are the raw metal prices for platinum and palladium as a function of years. Platinum is almost like 2-3 times more expensive than palladium. This is palladium, this is platinum. Again, this is what's happening in the world. When the platinum prices rises, everybody's borrowing money from the banks, AIG, Wall Street, everybody's making money. The real estate prices are going up, people are buying houses, everybody's happy, win-win. 2 plus 2 is 5. That's what Wall Street does. 2 plus 2 makes 5 in Wall Street, at least. So that means $100 million golden parachutes for CEOs for a bankrupt company. So in 2008, Lehman Brothers closed down September, I think 11, 12, whatever, and you can see, boom, again, platinum prices go down, nobody buys cars. And people actually sells cars. So again, you can follow these things, and platinum price increases goes down. So the problem is, platinum works very nicely for emission control, but it's very expensive. If you can use palladium, 30% of the price of platinum. But you have to use special materials like perovskite, so Dr. Stoichik mentioned these miraculous materials used for superconductors, used for solar cells, like lead-based halides. And they've got very interesting oxygen vacancy chemistry. So they've got very mobile oxygen vacancies and oxide lines, which make them very interesting redox catalysts for oxidation reduction chemistry. And General Motors company in the science paper published that we can make new materials that they don't have platinum, but they have palladium instead. And they used two different materials, and they were wondering why they were working. So they published in Science, but they had absolutely no idea about why they were working. They published the activity, but they didn't have any mechanism study. So we worked with them for a couple of years, and we had published some papers with them. And we had an understanding of what palladium does. It stabilizes structure, decreases the max oxidation, and it also prevents the, for instance, in the cobalt centers, if you look at them, after you reduce them, cobalt goes crazy and it becomes irreversibly reduced. On the other hand, if you have palladium that actually kind of suppresses this irreversible total reduction of cobalt size, and cobalt leaves the structure of perovskite and makes cobalt oxide and cobalt metallic. Manganese is actually more stable but less active. So the dilemma was the following. General Motors came up with two materials, cobalt-based perovskites, very active but not stable. Manganese-based perovskites, very stable, not active. So you have to find a kind of agreement between them. And the obvious thing is, can you just engineer these things? And this is another master's thesis, just getting published right now. And we aware quite different types of mixed hybrid perovskites with different compositions, about 11 different compositions. And we looked at their structure, stability, max absorption, and even like electronic structure. Like we did some experiments in Daisy synchrotron in Hungary, and we have verified, we have actually concluded that the B site oxidation state is the key. If you can fine-tune the oxidation state of the B site to a particular, I would say, oxidation state, we also control the oxygen surplus amount on the surface, and you can actually optimize the activity. So you can see that this particular material, the cobalt to manganese ratio of 0.8 to 0.2 has a significantly higher oxidation capability, which is much better than anything published there. So this was worked on with General Motors in the past. So these are all thermal stuff. How much time do I have? I don't know. Am I done?
No, you still have.
How much time? Half an hour. Okay. So this is thermal chemistry. So in the car, exhaust runs between 200 to 300 Celsius. You've got the kinetics on your side. You can activate, you can go over the activation gate by turbo activation. But the problem is, what about in this room? So you've got polluted air in this room. We have nitrogen oxide, sulfur oxide, hydrocarbons. How can we clean the air in this room without thermal activation? So what would be, the help is this one, light, right? So you can do miracles with light, apparently. So can you actually get rid of nitric oxides by using light? And you can tell us it's under ambient conditions, room temperature, no thermal activation. And keep in mind that these nitrogen double bonds or triple bonds, they have like 600 kilojoules per mole. You have to activate them. You have to break them at room temperature. Serious business. Okay? And another problem is, that means if you're going to clean the air in this room, apparently you need a construction material that you will blend in with gypsum, blend in with paint, blend in with cement. It should be dirt cheap. It should be dirt. Right? You cannot make platinum calus and colored walls. So you should have a material which is about like $10 per kilogram or ton, something like that. Apparently you can do that. So keep it, remembering the Toyota technology for diesel emission control, we said, why can't we use a similar approach, but replace the platinum redox site with a fluorocalus? One of the most, I'd say, commonly used, not straightforward, but commonly used oxidation callus, which is titanium. Titanium is a very well-known callus to do oxidation fluorocatalysis. That means if you have volatile organic compounds, it will oxidize it to CO2. Okay? The problem is if you have NO, and if you oxidize with air and water to NO2, this stuff is even more toxic than that. So you can oxidize this to NO2, and if you can capture this in solid state without letting it slip through to the air, very risky business. Because there is some chance that while we're trying to clean the air, we might intoxicate the air. But if you can manage that, if you can oxidize this rather than reducing, because reduction, forget about it. Forming the double, triple nitrogen, the room temperature, with high efficiency has not been demonstrated. If you can oxidize to NO2, then you can store using a basic nanoparticle like alkaline earth oxides, calcium oxide, magnesium oxide, in the form of nitrates and nitrites, and you can bingo, it will keep on sucking the nuts, it will form a four-shell structure, and every now and then if it rains, actually every month, if it rains once in a month, you're good. and I will show that it works for hours and days. This may not work in Qatar or in Egypt, so in the desert. You have to rain, you need rain for regeneration, so you have to get rid of the nitrate after saturation. But if you have some reasonable rain, this can work. So this is the setup that we have been using. So we're preparing a synthetic poison gas. We put NO, oxygen, nitrogen, and water controller. Then we pass it through a homemade Kelvin reactor. We've got the Kelvin's powder here, the shining light, and in dark, you see you feed 1 ppm of NO, which is about 50 times more toxic than typical air in this room. So you're really kind of giving me a hard time in our Kelvins. So if you in dark, you can see there's a little physical absorption, but when it occurs for a very short time, you saturate the surface and it goes to the normal level. That means your Kelvin's not doing anything in dark. As soon as you turn on the UV light, zoom. So you can significantly get rid of the NOx, and it goes for hours and days. As long as you have good light for days, you can store the NOx. And we even tried to start a company with this one with multiple people. It turns out that nobody cares about environment in Turkey, and people just want cheap construction materials. So
What kind of lamp?
pardon me? This is a typical UV-A lamp with 365 millimeter typical wavelength, but this also works invisible. I will give some examples. So we try to just have fun with these materials. We try to make different shape-defined nanoparticles and microstructures of titanium, like polymer coating, like these are polymers coated with titanium. We're still using some biotemplates like plant materials. We use some membranes, nanofibers, or polypeptides, and so forth. One example, very simple. Mine would take a cobalt polymer microsphere, coated with sol-gel chemistry titanium. You get the titanium microspheres inside of the polymer, burn it off, you get these micro rolls. The idea is like, can you have some light, the kind of confinement? Can you do more chemistry inside the cavity? Doesn't work that well, but it's okay. Nowadays, we have been using some interesting materials. So these are pollen spores, which are about 10 microns in size. They have brilliantly nice, pretty structures, very difficult to synthesize. These are cellulosic materials, and you can coat them with titanium, burn off the cellulosic material, and after you burn off the material, you end up with this interesting titanium structure. Almost impossible to make from bottom type of synthesis. And you can decorate them with quantum dots, plasmonics, what interesting things, so we are working on this one. You can also coat them with graphite carbon nitride 3D material. We have done that too. I'll mention that. The thing about graphite carbon nitride, it's got a band gap of 2.5 dB. It works invisible. So titanium works nice in UV. It does have also this black with but we will talk about some of the problems. But the good thing is you can make these materials, very interesting materials, and you can actually coat them with perovskites in Syria, very interesting structures. And you can clean the typical organics, rhodamine, typical liquid phase organic oxidation, and you can also do gas phase NOx conversion. And this is not all. Actually, it turns out that nature is quite rich in terms of interesting structures. So there are all different types of interesting pollens that you can buy from Sigma, which are different companies. They're used for allergy research. They put on your skin and to test your allergic response, so you can buy them actually. And he actually coated all of these materials with titanium and different things, like carbon nitride. So they're interesting. Nanoparticles, gold, silver, 2000, so on and so forth. One possible thing is graphite carbon nitride, 2.5 dB band gap, 2D material, S-triad rings, visible active material, very interesting type of material, and we demonstrate that we can actually control the carbon and nitrogen bonding structure over here with different synthesis protocols, and they're active under visible light, and they're reducible. So this is the crucial principle thing, and we're continuing on this one. What we're doing right now, this is Sean McWhorter's, one of my students' thesis, that you can further improve the surface activity by functionalizing these surfaces using thermal and photocatalytic means. For instance, you can generate some special surface function goods on titanium and/or graphite carbon nitride. For instance, you can put some oxygenates, alcohols, aldehydes, acids. Glycerol works very nicely. Then you can treat them with illumination, UV light. You break some of the bonds, you generate new chemical functionality, you heat them, calcine them, and make the proper surface functionality. And it turns out that you can significantly improve surface activity. And this is something that we are working on. This centered master's thesis just defended last week. What's interesting is titanium. Probably you guys have this titanium work like calculated the word titanium. And they say that this is the environmental friendly material and they use it for air pollution control. If you that's fine. You get CO2 plus water from volatile organics, oxygenate, that's fine. The problem if you have nitrogen oxides, this Dinox index is an indicator for total air pollution. You know, I told you that NO-based conversion is what we want, NO2 generation is not what we want. So if you get this Dinox index, which is the net pollution effect, if this is negative, that means you're actually polluting the air, rather than just basically abatement of the air pollution. Titania at whole levels actually is polluting the air in terms of NOx. So in the literature, this was just, they're just going to publish something. So actually, titania for NOx emission is not the way to go. And if you couple that with special type of mixed oxides, like alternating oxides, you can get closer to the NOx index. You can actually clean the air using titanium verified or titanium modified materials. So this is all fossil fuels. Nice. Can we go beyond the fossil fuels? Can we do more? Dr. Serge mentioned, for instance, some ideas about formic acid. I'll mention that. So bioethanol or biodiesel is something big. You can take cellulosic materials, not corn anymore, because corn gives you the food fuel dilemma. But you can take cellulosic materials, you can take catalysts, and you can convert them into alcohols. You can put them in your car, nice fuels. The problem is burning alcohol is one of the most primitive things that we can do in the chemical. So burning chemicals is primitive. It's useful, but it's primitive. As chemists, we can do much better than burning things. So if you convert them to more valuable chemicals, esters, aldehydes, you can make much more relevant, much more basically economically valuable things. And gold turns out to be an excellent selective oxidation, partial oxidation catalyst, or oxidative coupling catalyst. And the idea is that the intermediates that you form during the total oxidation series are not stable on the surface. So for instance, once you just have an oxidative coupling of alcohol to an alkoxide, attacking to an alpha carbon, from an ester, this ester has very limited absorption energy, so it just dissolves, which means you cut down the oxidation line and you can select for oxidation to esters. And gold is one of the unique chemicals, the unique chemicals that can do that. So we have been working on this one. The idea was, what is this oxygen doing on the surface? Is it on the surface? Is it in the subsurface? Or is it coming from the bottom? And we've actually verified using mass spectroscopy experiments by generating atomic oxygen using ozone absorption on sealed precipitate. I will just cut the story short, and he will, we're just going to publish this over the week, so we'll publish. What we verified is that if you generate these subsurface gold, subsurface oxygen, atomic oxygen on gold, this doesn't give you a significant reaction for forming esters from alcohols. If you have some subsurface and surface oxygen atoms, these are oxygen atoms, not oxygen molecules. It has limited activity. If you just cut down the subsurface oxygen and make only surface oxygen, you get like relatively high activity to oxidative coupling or partial oxidation to esters, which is money. But if you just increase the coverage too much, you can form like a 2 monolayer gold oxide, which is completely inactive. It only forms total oxidation, which is burning the fuel, complete waste of material. So we can actually really understand atom by atom, or at least in terms of locations, how these atomic oxygens are taking place in the partial oxidation chemistry using surface science. And we can even just use it for other things, like for instance, ammonia oxidation to nitrogen, which is also relevant to emission control. This is also something that we're going to be publishing. You get ammonia in the car generated, which is not also that much wanted, environmental toxic. If you put a bit of gold, you can actually convert it to nitrogen. And you just, give us some ideas about the mechanism. Probably I got like 10 minutes or something, so I can count, so I can have time. So, can we break the fossil fuel with hydrogen? So, definitely that's doable. We've got a long time, still a long time for hydrogen. It's commercialized, but not mass produced anymore. So, what we can do with this kind of things is probably this picture. So, Dr. Serge, you mentioned this one. You can take CO2, you can reduce that to any kind of oxygen reaction. Now, these people are using diesel. Last month was published in Nature $10,000 China. They made gasoline with 73% efficiency from CO2, and they licensed them. So it's coming. It's a big thing. CO2 to methanol, CO2 to gasoline, C5, C12. In Turkey, Tüpraş is doing a lot of work on this one as well. Refining companies. So what we can do is, if you have oxygenates like formic acid or anything, you can actually get the hydrogen from formic acid. And using two different pathways, this is the preferred pathway, generation of hydrogen with CO2. CO2 is nice, it doesn't bind to your palladium catalyst, it doesn't poison it. Dehydrogenation is what you want. However, there's a competing route, which is carbon monoxide formation with water, dehydration. even ppm levels of CO. Think about it. You know, like if you have less than a few tenths of percentiles of CO, it will kill your cells. So you need very high selectivity. Here's people. In 2015, we published a record high activity on formic acid dehydrogenation, and these were at this time the best materials published in different journals. We sent this to Nature Chemistry. The editor said this is not relevant to this journal, and then it was published in ACS Catalyst, which is also a nice journal. The thing is, you can see that they're all different types of catalysts, and they're quite, dissimilar. Cobalt, gold, palladium, like on carbon, on reduced graphic oxide, graphene oxide, on DNA, on metal oxide. The problem is that these are entirely different catalysts, and nobody knows why they work, why they fail. So we have done a bit of spectroscopy on these things, and we have verified the following. If you take palladium, the active site, and if you blend it with silver, very small amount, less than 10%, and if you make a bimetallic catalyst, the poison CO doesn't absorb on this palladium silver anymore, because silver changes electronically the d-electron states of palladium, and it actually donates electrons to CO, and it gets to anti-bonding, and you actually loosen the CO bond and also palladium carbon bond, and that means you decrease the affinity of CO to the active site. So then what does CO do? It goes to the sacrificial site, which we add as manganese oxide. It forms carbonates. That means this promoter is a sacrificial carbon CO suction unit. It sucks the poison, keeps the active site basically clean of CO, and by using infrared spectroscopy, in situ infrared spectroscopy, we've actually verified that these manganese oxide and palladium silver bimetallic nanoparticles work like a charm. They're not only active, but they're also tolerant for CO poison. And now we even just put the game from one level high. We made the trimetallic engineering of these catalysts, and now we've got the record high material again. This is to be published hopefully next month. And by using spectroscopy, you can see that the CO absorption is going down significantly, and also frequencies are shifting, which is an indication of CO absorption strength going down. We can actually say that this catalyst is feeling like more over to CO absorption. And you can see this is not rocket science, these are simple things here, right? But this is rocket science. What we do nowadays with a Turkish company called Roketsan. These guys, as the name suggests, they're making rockets, military company. And they approached us 3 years ago. I was in touch with my 4-day vacation on the beach. I got a call from them. I said I had to pick it up. I picked it up. They told me that there's a national program called National Satellite Program. They're trying to make a national satellite, communication satellite. And Roketsan is designing a propulsion system. The problem is, normally you use hydrogen, a very unstable fuel. It's called monopropellant. We don't use it for other things. Hydrogen is toxic and not stable, very difficult to handle, safety issues. And you can replace this with new ionic liquids. This is ammonium dinichromide type of ionic liquids. And they're stable, and they're only activated if you have a catalyst. So they're safe. You can heat them until 170 Celsius, you can shake them, drop them, they will not explode until you just activate the catalyst. The only problem is, they don't know what the fuel should be, because you cannot buy this. Nobody sells the ADM. You have to synthesize it with some other formulations. And nobody sells the catalyst. For instance, Roketsan company tried to buy a sample, which is 20 grams. They paid about 25,000 euros for 20 grams of sample of catalyst. Just for checking those numbers. So it's very expensive technology, nobody wants to sell. And they said, can you make a catalyst that that will decompose these ionic liquids in the absence of oxygen? Because this is supposed to work in space. Okay? Very difficult catalysis. This is explosion catalysis, chain reaction. Local temperature goes to about 1,000 Celsius temporarily. That means you need a nanosystem that will survive 1,000 Celsius in space for 10 years. This is not to take the satellite from Earth to orbit. That's a different propulsion system. This is for maneuvering. You've got 6 different, or 3, here you've got 3 motors. So it does poof, poof, poof in the orbit, and it actually controls the inertia of the satellite. So it doesn't run continuously. It's a discrete system, but it should run 10 years. And the good thing is they don't have money requirements, so cost is not an issue. It's a very expensive system. Even if you put like $100,000 catalyst, they're okay. Because the mission is much more expensive than that. And we started work with that. We just generated some data. They were very happy. So actually, hopefully next week, we are renewing the contract. The budget is increasing about 30 times. And hopefully we will start a 2-year phase where we will work on these kind of things. Actually, surprisingly, the chemistry is very similar to emission control systems. We don't tell them to look at something. But actually, it's oxidation chemistry into the absolute oxygen. So what we use is we actually add some cereal and lactone. These are oxygen pumps. That means they can take oxygen into their lattice and they can pump out the oxygen from the lattice by generating some oxygen vacancies. So you get microgroups in the field. When it decomposes, oxygen is stored in the solid. And then when you're deficient of oxygen, solid just kicks out oxygen and you can actually do redox chemistry in space, in the actual oxygen. And it works like relatively fine. There's all different types of ideas that use perovskites, perovskite, biometallic, so that is there. So with that, I will just mention that we are just a relatively young group. We are trying to do catalysis in Turkey. These are much more simplifying work than the excellent stuff that we listen to in the morning. So these are basically our initial efforts, so there's a long way to go. As I said, I'm just talking about the stuff. These are the guys who are doing the microscope in the lab, and this is where the money comes. And our collaborators, some of them are here. And if you're interested, this kind of research, come to our labs, good opportunity, hang around the whole month, talk to us, email us. We're looking for always some good talent. Thank you very much.
Do you have any questions?
First, if you go back to Enoch's catalyst is power focus. I mean, there was a cartoon, but maybe I missed it. What is the role of platinum there?
It's the redox active side. So let me just go back there. Probably referring to this one. This one, right?
Yes.
So here, platinum can do two different things. Under oxidizing the environment, platinum can do oxidation. So in the regular fuel efficiency mode, you get a lot of oxygen, which means in the diesel engine you get air injection, or there's a valve, and the fuel valve. In fuel saving mode, you get a lot of air and little fuel. And then under those conditions, nitrogen oxide makes nitric oxide, and platinum with oxygen oxidizes NO into NO2. Okay? And this NO2, both through surface diffusion and gas phase transport, it gets on the alkaline metal oxides and stored as a core shell bearing nitrate bearing oxide nanofiber. So then, this takes about 120 seconds. Then for about 5 seconds, the artificial intelligence, there's actually a software which does that, it opens just a bit 5% more fuel. And then you get hydrocarbons. When you have hydrocarbons, this nitrate starts to oxidize the hydrocarbons, so that means you use hydrocarbons as reducing agents.
But this is the point which I don't understand.
And you get
how does this nitrate oxidize the hydrocarbons?
It actually happens on the platinum. So the max actually, the chemical potential of max changes in the presence of absorption of hydrocarbons. This is called the max rate. So this barium nitrate surface shell almost explodes. And nitrate decomposes into NO plus oxygen and NO2 plus oxygen. And at this time,
why doesn't do it here?
Because you don't have hydrocarbons. You get very little hydrocarbons. Hydrocarbons are completely combusted to CO2. So this happens on the platinum in the presence of the hydrocarbon. You should have excess hydrocarbon. So you believe in excess fuel. That's your reducing reason.
I thought CO2 is every time, everywhere.
That's right, CO2 is there every time, but their ratios and compositions are different. So here, you form CO2, so all of the hydrocarbons. In this picture, I'm not talking about hydrocarbons because they're completely combusted to CO2 and water. So there is no extra reducing agent to reduce mass, because you don't want to use a lot of fuel. So you use a small amount of fuel and you combust all the fuel to CO2. So here you store the mass. And here the excess hydrocarbons, not much, just a little bit. On the platinum, you can do max reduction using hydrocarbons, CO, with some, this is low oxygenation, so you also decrease the oxygen level, so you don't have complete combustion. So in partial oxidation conditions, you use those reducing agents to actually reduce the max to nitrogen. So what you want to do,
If you make the picture complete and realistic, of course you have to put on the left hand side also CH, also CO, also CO2.
exactly,
No, they are artificially missing in this model.
That's right, that's right. So of course, this is more for professionals and people in the field. You're perfectly right. If you want to really understand that, obviously we are saying that you've got SO2 here, you've got hydrocarbons here, you've got CO here, you've got CO2 here. Obviously those chemicals are there. However, this is more focusing on the active chemicals and true origins.
Is it now a speculative theory or
Actually, this is,
you know
this has been established with mass spectroscopy and earth different techniques, Raman, infrared, this has been established. This was first actually put into the market without even publications by Toyota in 1995. Then the patents and publications came later, so it's kind of revolutionary at the time. But now it's all established experimentally, so we measure these mass spec on different conditions. There's no doubt that these species are there. Using infrared gas phase analyzers, quantitative ppm, we can measure all these. With nitrogen, you need a mass spec.
because there must be a really fine balance of this
Exactly.
nitride exploding,
Exactly.
nitride
Exactly.
I want to see this
Exactly.
equilibrium constant. I don't like this yet.
That's
No,
perfectly
it's
fine.
fine, I mean-
Mark Kinnick's analysis has been there, so the reaction pathways, partial grade constants for different steps, so
Is the pressure both sides always the same?
of course the car runs almost in atmospheric conditions, more or less. So the
So these two
exhaust
cycles have the same thermodynamics.
yeah, temperature changes from this is called lean and rich condition. Temperature changes slightly, but kind of, but not exactly the same. They're slightly different.
Interesting.
Yeah. So the nice thing is, we want to do reduction, but rather than reduction, you do oxidation. So you want to get rid of something by doing first oxidation and then reduction. So this is the nice thing. It works fine for small cars. For big engines, you need a special reducing agent like ammonia. This is called selective catalytic reduction. This is called Maxwell technology. This works fine for sedan cars with medium scale. If you go to large scale, you will just need a special reducing agent like ammonia, special injection.
And this is molecular spectrometry.
Actually, always using far away working like for this using this is a combination with other things I haven't mentioned. But now this is all over the place.
Any more questions?
I have a short question. You showed several features with very nice wall structures.
Yeah.
And you mentioned about the conformal working of these structures.
Yes.
Which technique have you used for?
Actually, it's extremely simple soil gel chemistry. We have used different things, but the ones I'm showing are extremely simple. We can take titanium isoproposite, we can control the pH, and we can do very simple soil gel chemistry. And this is published. We can check the publications. All of the papers are on our website. You just type Özensoy to Google. All the papers are directly available by PDF. So this is done by simple soil gel chemistry. You get titanium isoproposite, you alcohol neutral, you control the pH by a buffer, and you control the loading. And then by controlling calcination environments, oxygen and temperature, you can get even control NFA's rutile ratio. So you can actually XRD and Raman. You don't only coat them in titanium, but you actually play with the total band gap by calcination, and you can control NFA's rutile ratio. Otherwise, you don't have to optimize the catalytic activity. So it's actually very simple.
Did you study there?
That's right. So we have verified activity in frequent phase, also gas phase. So they're not like extremely active, but they're definitely interesting, and we're actually improving the activity using visible light. What I didn't mention, the solar spectrum, we've got like 5% UV and 40% visible. So if you get access to visible wave and region, you're going to be in better shape, and with gravity carbon nitride, actually we can do that.
Are they being used?
Yes, so let me see why I have the date over here. Not in this picture, but you can actually use them. So it's very carbonic data is there, so you can use them. For rotary be they're nice, for metallurgy, they're nice, but in certain cases, these are for physical laboratory, yes.
The slide where you use zirconium oxide as a layer to protect barium oxide by mixing with titanium oxide.
Yes.
So my question is, if there is a layer, then how do they interact? And if they don't interact, so if there is a zirconium oxide layer between barium
It's
oxide,
not a layer. What we make is actually a ternary mixed oxide. So in that particular case, we have an oxide solution which is amorphous.
yeah.
They are not layered materials.
Okay.
We prepare them in a special way that actually we don't want them to be crystalline. So you still have barium oxide domains, but they're amorphous, small particles, not well-defined. XRD patterns are completely amorphous.
Okay.
So in that particular case, you avoid or prevent the formation of crystallites. Because with possible brightening and all that jazz, those crystallites eventually thermodynamically get together and mix. But if you can limit the diffusion by mixing it almost like a glass, a ternary glass of mixed oxides, you can prevent the diffusion of cations, and then you can limit the formation of crystal growth.
So when you used it, how long does the lifetime of this catalyst increase?
We didn't do a lifetime analysis. However, we have run them under real conditions, and they can beat the Toyota catalyst with a reasonable, I would say, amount. Go back to this one. And what's very important is not so this is the fresh catalyst. This is how much you can store the NOx. That is how can you get it over the ammonia here. This is the conventional Toyota catalyst. So you can see there is about, I would say, 30% improvement for the fresh catalyst. What is more important is that after you poison this with SOx, it kills itself. But after you regenerate it, and this is reducible many times, like this has been done by about 10 cycles, it works even better. And the reason is that a bit of sulfur is nice for the structure because it generates some Lewis acidity on the surface. NOx, nitric oxide, nitrogen dioxide, these are acidic species. So if you make surface less basic or more acidic, that means you actually prevent the sulfur dioxide, which is also an acidic component. You prevent heat of the absorption. Okay, so the improvement is real and reproducible, and in fact, I think it is significant. So we can actually beat the conventional catalyst significantly.
Any more questions?
Can this titanium-based catalyst be used for, or did you try to use for other environmental pollutants, like, for example, pesticides or explosives, for example?
Could be used, yeah. For any kind of oxidation chemistry that could be used. I mean, literature is full of those kind of studies. This is just proof of principle showing that it can work. Our emphasis was nitric oxides, where you don't need oxidation chemistry, you need reduction type of work, where you have to just have a capture process. So definitely these would work in oxidation processes. So these liquid phase experiments that we use, oxidation of metals, they indicate that they do oxidation reactions rapidly. You can use drug composition in polluted water, that sort of things.
Okay, one more question that we
Which give you the best result, fiber or tube or particle? Which
You got the best results with no shape.
no shape?
That's right. So when you just play with the crystal structure without the shape-defined, I would say, catalyst. So when you try to control the shape, it turns out that activity always goes down. So you never achieve a nice-looking catalyst, which is also reactive. So the best catalysts, they look terrible. They have no specific shapes. They are very complex in their nature. They have well-defined crystal structures. So they have a lot of different types of active sites. I would say ugly-looking catalysts, they're heterojunctions. There are specific interfaces that are different types of titanium, different oxygen weights, different band gaps, they form these heterojunctions. And they might be quite active. They're not shape-defined. So shape-defined materials are nice. They're hoping to use these bio-inspired, bio-templated materials with some activity, but it's coming. So visible light will actually demonstrate their activity, which can surpass the UV activities. Probably the plant
actually, I have a question, so you may allow me to ask about that. the general mechanism of filtering the engine exhaust.
Yeah, I mean, Dr. Sertic actually pointed out crash course in emission control systems. You don't have only what I showed. So when you have incoming, when you press on the gas in your car, in a diesel car, the first thing that we have is a special catalyst called diesel oxidation catalyst. So here, what you do, this is also diesel particulate filtering. You put particles like carbon sulfides. This is a catalytic reactor that looks like this. Okay. So you have basically gas comes in. These are basically pores. So it comes in over here, and particles they get stored. These are carbon sulfide-based micron-sized particles, and then you burn them off. The first step is burning off the particles, particle matter, less than 5 micron size. The second reactor is what we can call LNT or NSR. This is the Toyota technology. Here, what we do is actually we take NO and NO2 and we store it in the form of nitrates on the surface. And absorb nitrates. Okay? So then, in the breach cycle, when you absorb this one, there is a third catalyst. This can be called SCR, selective reduction. There's an ammonia injection system over here that works together with this one. There are oxygen sensors. There are pressure sensors, there are temperature sensors, there are about like 12 different sensors, all working parallel with a computer program. And these are 3 reactors working at the same time in serial mode. So then this ammonia is used as an extra, and you also generate ammonia here as well from the LNT system. And then just finally you get into nitrogen, CO2, and water with the heavy end. So there is not just one mechanism. There are 3 different reactors, and you can write literally tens of steps. And Dr. Sertic was right in terms of the complexity of the problem. It is extremely complicated. And the problem is driving conditions. If you go back while we were cooperating with General Motors, we have a different program. We have seen huge dyno tests. There are urban and highway driving cycles. There are different simulations of driving, like you drive a highway, constant speed, like 90 kilometers. Then you stop at the red light, then you go accelerate, decelerate, and everything changes as a function of driving cycle. Very complex business. Not very easy. But the thing is, if you buy a car, let's say you buy a Toyota Corolla car, in the United States it's like $50,000. About 10% of the car's value is catalyst raw material. 10% of the car. Think about the competition in the market. If you can reduce the cost by 70%, that's huge competition advantage. And the problem is the values fluctuate. And in precious metal PGM, platinum group metals fluctuate. So for instance, when we were talking to GM, they told us that they're actually buying and storing about like $100 million worth of platinum in the world. But they don't want to just, they can't change their engine design if the platinum goes like 10%, 20% in price. They cannot sell it for focus with the GM shape. So, very complex. So they're only dealing with one reactor, a certain part of the story is much more complicated.
Yes, so,